Good day, students. Welcome to Mathgotserved.com. In this clip, we're going to be going over problems 35 to 36 of the June 2016 Geometry Common Core Regents exam. All right, let's take a look at 35. It says quadrilateral ABCD with diagonals AC and BD that bisect each other, and angle 1 is congruent to angle 2. Prove that triangle ACD is an isosceles triangle and triangle AEB is a right triangle. All right, two things you want to keep in mind to help us prove these two statements is that number one, the first one has to do with isosceles triangles. Okay, so one of the property of isosceles triangles is that base angles are congruent. Keep that in mind. Rhombuses. One thing you want to keep in mind out of the many properties of rhombuses is that diagonals bisect each other at right angles. Okay. All right, so before you start your proof, you should have a general idea of the direction in which you're going. You should have a plan as to how to end up with the indicated conclusion. All right, so we're going to break the proofs up into two parts. So part one, we want to prove that triangle ACD is an isosceles triangle. So what are we trying to prove here? In order to show that triangle ACD, this triangle right here, ACD, is isosceles, all we just have to do is we just have to show that these base angles are congruent. If we can show that these base angles are congruent, then we can conclude that the triangle is isosceles, because one of the properties of isosceles triangles is that base angles are congruent. Okay, so that's the goal. You always want to have a goal in mind before you start your proof, so you're not going all over the place, but have a direction. Okay, all right, so statement and reason. Okay, so our goal again is to try to show that these two base angles are congruent. So to aid us in accomplishing that, I'm going to label these angles with numbers so I don't keep writing letters over and over again to represent the angles. That's going to waste a lot of time, okay? So let's call this angle 4 and angle 3. So angle 1, 2, 3, 4 equals angle 3. Okay, now let's see. We're going to start by writing down what's given to us, okay? Now, one fact that's provided to us is that these two diagonals, AC and BD, bisect each other, okay? Now, what does that tell us about the whole scenario? If you have two diagonals that bisect each other, then they're basically diagonals of a parallelogram, okay? And then if we can draw that conclusion, then we can start talking about alternate interior angles of a parallelogram. So that's congruent to that. This is congruent to that. Basically, all four angles are congruent, okay? And that will basically help me accomplish our first goal, which is to show that triangle ACD is isosceles, okay? So that's the general idea there. All right, so let's start with the first statement. Diagonals AC and BD bisect each other. Bisect each other. That's a given. All right. So what can we deduce from this situation right here? Since diagonals bisect each other, these diagonals are basically diagonals of a parallelogram. Okay. So we can deduce the fact that quadrilateral A, B, C, D is a parallelogram, okay? And the reason is because diagonals of a parallelogram bisect each other, okay? Diagonals of a parallelogram bisect each other. All right. So what can we draw here? How can we annotate what we have so far? Well, if this is a parallelogram, we're looking at these angles, so we know that this side BC is parallel to AD, and AB is parallel to CD. It's good to label your diagram so you have a visual cue as to what you've accomplished thus far. Okay, now let's move on to the next part, which is basically putting down what we wrote, sketched here in our proof. Okay, so we have we're looking at this angle right here, so we're going to be looking at AD and CD. So AD, segment AD is parallel, okay, AD is parallel to CD. The reason is because opposite sides of a parallelogram are parallel, right? So opposite sides of a parallelogram are parallel. So makes them a parallelogram, okay? Okay, now that we have that, we can now start talking about the angles. Statement 4, we can say that we have a parallel line, a pair of parallel lines BC and AD, and we have a transversal here, okay? And we also have a transversal there. So let's look at that transversal AC. Angle 1 and angle 3 are alternate interior angles. The same applies with angle 2 and angle 4, okay? So let's write down some statements using that fact. So we're going to say angle 1 is congruent to angle 3. We can also say that angle 2 is congruent to angle 4. Now, why can I make these two statements in the same line? Well, it is because they have exactly the same reason, okay? If they have different reasons, then you may not cluster them together in the same statement. That will be inaccurate. You have to break them up. So what's the reason that enables me to conclude that angle 1 is congruent to angle 3 and angle 2 is congruent to angle 4? They are alternate interior angles, okay? So if two parallel lines are cut by transversal, alternate interior angles are congruent, okay? So let's write that down. When parallel lines are cut by a transversal, alternate interior angles are congruent, okay? So let's go ahead and mark what we just wrote on our diagram to help us. So angle 1 is congruent to angle 3, and angle 2 is congruent to angle 4. Okay? So we can make a substitution here. We know the following. We know that angle 1 is congruent to angle 2, right? So let's write that down. Angle 1 is congruent to angle 2. Now how do we know that angle 1 is congruent to angle 2? Well, guess what? If you go back to the original problem, it's provided to us as given. I didn't want to put it in the start because I wanted to put it when I'm going to use it. All right, so angle 1 is congruent to angle 2. That's a given. So with this statement, I can make two substitutions. First one, I can replace, you see this 1 right here? I can take angle 2 and plug it right here. So I have angle 2 is congruent to angle 3, which shows our proof. Okay? I can also take angle 1 and plug it in right here. Bam. Okay? Which shows that angle 1 is congruent to angle 4. Okay? And basically, in conclusion, I can say that all 4 angles are congruent by substitution, which will be assisting us in the next part. Okay? So let me write down the statements I just made. With this given situation here, line 6, I can conclude that angle 1 is congruent to angle 4, and angle 2 is congruent to angle 3. Okay? And the reason is by substitution. Okay? And then by substitution, again, I can say that angle 1 is congruent to angle 2, and it's congruent to angle 3, and it's congruent to angle 4. Okay? That's by substitution. Just putting everything together. Okay? All right. Now, from line 6, I can automatically conclude that triangle ACD is an isosceles triangle. All right? So line 8, triangle ACD is an isosceles triangle. Now, what's the reason? How can I arrive at that conclusion? Well, it is because of the property of isosceles triangles we talked about earlier, which is that base angles of an isosceles triangle are congruent. Okay? Base angles, angle 2 and 3, see right here, angle 2 and 3 are the base angles of ACD. Base angles of an isosceles triangle are what? Are congruent. Okay? All right, so that completes the first part. All right, now let's take a look at the second part. So part 2, part 2, what are we doing here? We want to prove that triangle AEB as a right triangle. AEB is a right triangle, okay? So if we can just show that one of the angles in triangle ABC is 90 degrees, then we're done. Okay, so what's the plan for that? Well, we talked about it earlier that the diagonals of rhombuses bisect each other, intersect each other at 90 degrees. They're perpendicular bisectors. So the plan here, first of all, is to show that this is a rhombus. Okay? If we can show that this is a rhombus, then we can argue that the diagonals bisect each other at 90 degrees, which makes this angle right here 90 degrees, and that's contained in triangle AEB, which makes triangle AEB a right triangle. Okay? So that's a plan of attack. Try to show that this is a rhombus. Now, how can we show that this is a rhombus? Well, we already know that these are isosceles triangles, right? So this is congruent to that, and this is congruent to that. But guess what? These two isosceles triangles are congruent. Okay? We can use ASA, congruency postulate, to show that these two triangles are congruent. And then, since they are isosceles triangles that are both congruent, then all four sides are congruent, which makes this a rhombus. Okay, so we're going to use the congruency of these two triangles and substitution to show that this is a rhombus with all four congruent sides. We talk about diagonals intersecting at 90 degrees, which makes AEB, an angle that has one of those perpendicular angles, a right triangle. Okay, so that's the plan of attack. Okay, so let's go ahead and get started. Statement and reason. All right, so goal number 1 is to show that these two triangles are congruent. So we're going to be taking some things that we got from the previous step. So let me start from, that was 8. So this is a continuation. We can call this 9. So I can refer to a step in my previous proof. So we're going to say that angle 1 is congruent to angle 2 and angle 3 is congruent to angle 4. Okay, so let's put them in, angle 3 and angle 4. Okay, I'm going to switch this around. I got to keep it in order. So angle 4 is congruent to angle 3 from line, wait a minute, where is it? Okay, from line 7. So from line 7, we already showed that all 4 of them are congruent, so we can pick any pair and they'll be congruent to each other. Okay, so in my proof using ASA, I already have A. Oh, actually, I have A and I also have another A. Okay, I have an A and then another A. So I need an S. Where is the S that can help me show that these two triangles are congruent to each other? Do you see it? I need the S. The S has to be between the two angles, right? So for step 10, we're going to say that AC is congruent to AC. This is based on the reflexive property of what? Of congruence. Okay? So I have my S. Nice. So now I can say that triangle ADC is congruent to triangle ADCCBA. Alright, by the ASE congruency postulate. Okay. Alright, so we show that these two triangles are congruent to each other. Okay, so now we have two isosceles triangles. So what can we say concerning the two isosceles triangles? Well, we can say that AD, side AD is congruent to DC, right? In this isosceles triangle right here. And then we also know that AB is congruent to BC. Since they're both congruent triangles, ABC is also an isosceles triangle, okay? So whatever property A has, the other triangle has the same property too. So this is because statement 12, oh snap, I didn't put the numbers here. This is because the sides of an isosceles triangle are congruent, okay? The sides of both isosceles triangles are what? Are congruent, okay? All right, but what else do we know though? From the original statement, we concluded that this is a parallelogram, right? So since it's a parallelogram, not only are adjacent angles going to be congruent here, but not only are adjacent sides going to be congruent here, but opposite sides will be congruent also, because opposite sides of a parallelogram are congruent, okay? So from 13, for 13, we can also say that AD is congruent to BC, the side opposite it, and AB is congruent to CD, the side opposite it, because of what? Opposite sides of a parallelogram are congruent. Remember, we have already established in the previous proof that ABCD is a parallelogram in step 2, okay? So that's basically what we're running off of right now. Now, since adjacent angles are congruent and opposite angles are congruent, guess what? Since adjacent sides and angles are congruent, that automatically means that all 4 sides are congruent, okay? By substitution. So 14, we can say that AD is congruent to DC. Okay, AD is congruent to DC. We already know that. DC is congruent to BC. BC is congruent to BC because we know BC is congruent to AD and AD is congruent to DC. So by substitution, we have that. And then BC is congruent to AB because we know that AD is congruent to CD to DC. Oh, it's already stated here. AB is congruent to BC because this is an isosceles triangle. Okay, so by substitution, we can conclude that all four sides are congruent. So 14 by substitution. So what have we just accomplished right now? Why are we trying to show that all four sides are congruent? Well, if we show that all four sides of this quadrilateral, this parallelogram, all four sides are congruent, then we have a special quadrilateral, a special type of parallelogram. A parallelogram with all four sides congruent is known as a rhombus. Okay, so that's what we've been going through all this problem, all this headache to try to prove. Okay, so quadrilateral ABCD is a rhombus. Okay, and how do we know that that is the case? Well, all four sides, or we can say an equilateral parallelogram is a rhombus. Okay, so a parallelogram that has all four sides congruent is automatically a rhombus. Okay. All right, we're almost there. So let's not forget the goal. The goal is to show that this is a right triangle. Okay. So if we can show that this is a right angle, then we can arrive at the conclusion. So step number 16 has to do with a cool thing that happens with the diagonal of rhombuses, which is basically that diagonals of rhombuses are perpendicular. Okay, so let's write that down. What are the diagonals? AC and BD. So AC is perpendicular. AC is perpendicular to BD. Okay, what's the reason? Diagonals of rhombuses are perpendicular. Okay. All right. Next, what do we know about angle BEA? Angle BEA is a right angle. And how do we know that? We know that because perpendicular lines form right angles. Okay, so perpendicular lines form right angles. And then what do we know about a triangle that contains a right angle? A triangle that contains a right angle is a right triangle, right? So so we can finish it off. Statement 18, which is what we're asked to show, triangle AEB is a right triangle. How do we know that? Well, it is because triangle AEB contains a right angle. All right, let me correct that real quick. So right triangles contain right angles. So right triangles contain a right angle. Okay, so that's basically that. The right angle we're talking about here is angle BEA, which is contained in triangle AEB. So that automatically makes triangle AEB a right triangle. All right, let's take a look at question 36, the last one in this on this test. It says a water glass can be modeled by a truncated right cone. That's a cone which is cut parallel to its base as shown below. So you have a right cone right here that's truncated at at a section that's parallel to the base. The diameter of the top of the glass is 3 inches. The diameter at the bottom of the glass is 2 inches, and the height of the glass is 5 inches. Okay. First question: the base with a diameter of 2 inches must be parallel to the base with the diameter of 3 inches in order to find the height of the cone. Explain why. Okay, so in order to help us understand what's going on, I just basically got a two-dimensional snapshot of this three-dimensional figure. So what we have here is you have a triangle that's been split down the center. Not down the center, but just with a segment right here, okay? Somewhere in between the base and the vertex. So the statement here is that in order to be able to determine the height of the cone, this segment right here must be parallel to this segment. So let's label it so it's easy to make reference to. So we're gonna label it in the following order. So let's call this A, B, C. So that's a bigger triangle. That's like the entire cone. And then you have, let's call it D, E right here. Okay. So the goal is the statement is that in order to be able to solve this scenario right here, ED has to be parallel to CB. Okay. So why must that be the case? Well, that must be the case because we have to establish a relationship between two triangles. And the only way we can relate these two triangles, A, DE, and ABC, is if they are similar. Okay, so if you have a similarity relationship between these two triangles, then guess what? Corresponding sides must be in proportion, which automatically follows that the bases have to be parallel. Okay, so if these bases are parallel, then that's consistent with the similarity relationship between these two that can help us to set up a proportion relationship between these two triangles. Okay, all right, so let's write it down in order to find the height of the cone. In order to find the height of the cone, the two bases must be parallel because this creates a similarity relationship between triangle ABC and ADE, and this enables us to set up proportions that can be solved to find the height the height of the cone. Okay, so the goal here is being able to set up a proportion, and if these two triangles are similar, which can be deduced from the parallel nature of the bases, then we can set up a proportion and find out what the height of the cone is. All right, let's move on to the next part. It says determine and state in inches the height of the larger cone. So we're looking for this big one right here, the height of this big cone. Okay, so basically, let me label this. Let's call this basically the altitude of this triangle. Okay, so the length of this middle segment right here. So just to help you understand the two-dimensional representation, I'm going to label both of them, the larger cone and this triangle right here, so you can basically see how I'm setting up and solving the triangle. Okay, all right, so the bigger diameter is 3. Okay, so from here to here is 3 inches. So that means the top right here, segment CB is going to be 3. Okay, so that's 3 inches. Remember, it's the diameter, not the radius. Okay, so you got to be careful with that. All right, so that's the diameter of the base. And then the smaller diameter right here. So from here to here, that diameter is 2 inches. Okay, so from here to here is 2 inches. So hopefully you can see what that corresponds to in the two-dimensional representation. Segment ED is going to be 2 inches long. Okay, so from here to here, it's not drawn to scale. Okay, so that's going to be 2 inches. Okay, so remember that these two triangles are similar. So we have a proportional relationship between corresponding sides. So side CB, the side right here, corresponds to side ED. Okay, what are we looking for? We're looking for the height. So we're looking for how tall is it? How tall is the larger cone from here to here? Okay, that is what we're looking for. Okay, but we know that the height of the glass is, what did it say the height of the glass was? I totally forgot. Oh, 5 inches. Perfect. So the height of the glass is 5 inches. Okay, so this segment right here, this portion right here, is 5 inches. Okay, and guess what this portion down here is? What is that? We don't know. If we add 5 to whatever that is, then that will be the height of the cone. So since it is an unknown, let's just call it x. Okay? All right. So in our triangle, this portion right here, this is 5 and this is x. So we have two triangles. Okay? For the height of the smaller triangle, it's x, as you can see. And the altitude of the bigger triangle is the entire combination of the height of the water glass and the height of the smaller triangle. Do you know what that is? Do you know what the entire length measures? It is x plus 5. Okay, so you have this portion right here is x. Okay, and then this portion up here is 5. So the entire combined length is going to be the algebraic expression x plus 5. Okay? All right, so since corresponding sides are in proportion, we can set up the following equation. So we have, well, let me just write it in letters first. Oh, we can't do that. So let me use the numbers. So we have, well, I can just put in letters to just help you see what's going on. So I have A, B, C, D, E, F, G. Okay, so this is the statement I'm gonna say. Okay, CB, the base of the bigger triangle, over ED, the base of the smaller triangle, equals to AG, the altitude of the bigger triangle, divided by AF, the altitude of the smaller triangle. Okay, remember, when two triangles are similar, corresponding size and proportion, that's why I'm able to do this. Okay, so CB is 3, as you can see. ED is 2. Okay, I didn't put it in there, but this side right here is, oh yeah, it's right here. It's 2. AG is the entire length. The entire length is x plus 5. That's what AG is. Okay, so AG is x plus 5. And AF, the altitude of the smaller triangle, is x. So that's what we have. We have this proportion right here. Okay, so we're solving for x first, and then eventually we want to remember what we're asked to find. We're asked to find the height of the entire cone. Okay, so that's going to be AG. It's AG that we're going to be looking for. Okay, all right, so let's solve this for x first and then find out what AG is. So if you have a proportion like this, you cross multiply bottom left to top right. bottom right to top left. So that yields 3x equals, now don't forget, well, let me write it like this so we don't make any mistakes. Okay? Anytime you have parentheses, don't forget to distribute to both terms in the parentheses, 2x plus 10. To get x isolated, you subtract 2x from both sides. And then you're left with x equals 10. Is this our answer? The answer is no. 10 is the height of the smaller triangle, or the cone that got cut off, okay? 5 is the height of the water glass. So the height of the entire cone is going to be a combination of the two, okay? So let's write that down. The height of the entire cone, the height of the actually larger cone, is x plus 5, which is 10 plus 5, which is 15 inches. So that's the height of the larger cone. All right, let's look at the last question. It says determine and state in inches the height, it says determine to the nearest tenth of a cubic inch the volume of the water glass. Okay, so we're going to be doing some algebra with volumes here in order to determine what's the volume of the water glass is. Okay, so this is what I was talking about. So what do we have here? Well, we have the larger cone, we have a smaller cone that was taken out, and then we have the water glass. Okay, so this is what we're going to be doing. We're going to be finding the volume of the larger cone, and then we're going to subtract the volume of the smaller cone. And guess what that gives us? It gives us the volume of the water glass. Okay, so all we just need are our formulas, the dimensions, the relevant dimensions, basically the height and the radii of the two of them, and then we'll compute their volumes, find the difference, and that will give us the volume of the water glass. Okay? All right, so let me organize my dimensions here so I don't get confused. We know that the diameter of the larger cone, this whole thing is 5, right? So the radius of the larger cone, I'm going to call it RL, is, well, actually, this is supposed to be 3, I'm sorry. The diameter of the larger cone is 3. And the radius of the larger cone is going to be half of that, which is 1.5. So the diameter of larger is 3, and the radius is 1.5. So let's call this larger. All right, and then the height. The height of the larger cone is 15. Remember, that's what we found in the previous problem. The height of the entire cone, that's 15, okay? All right, so that's that for the larger. That's what I'm going to be plugging into my formula. And then for the smaller cone, what do I know? Remember, the diameter of the smaller cone is 2, right? For the entire thing. So if the diameter of the smaller cone is 2, then what's the radius going to be? It's going to be half of that, right? Which is 1. What is the height of the smaller cone? That was our measure for x, right? This x that we found out right here, and that is 10. So the radius of the height of the smaller cone is 10 inches. All right, so radius 3, height is 15. That's for the larger cone. And then for the smaller cone, the radius is 1. So because you know the diameter is 2, right? So the radius is going to be 1. Just like this one has a radius of 1.5. And then this has a height of what? Has a height of 10. Okay? All right. Now we're good to go. What's the formula for the volume of a cone? It's a third of a volume of a cylinder with the same base, radius, and height, right? So it's going to be what volume of a cone is equal to 1/3 pi r squared h. All right, so we're going to use this formula right here. So volume of water glass is going to be volume of larger cone minus volume of smaller cone. All right, so we're going to go 1/3 pi times the radius of the larger cone is 1.5 times the height of the larger cone, which is 15. All right, so this tells you the volume of the larger cone, and then the smaller cone is 1/3. Square the radius there. Pi times the radius of the small cone, which is 1, squared times the height of the small cone, which is 10. Okay, so just simply plug all this into your calculator. All right, so you enter it in your calculator like that. 1/3 pi 1.5 squared times 15 minus 1/3 pi 1 squared times 10. Enter, you get 24.870941. So we were asked to round it to the nearest tenth. So basically one decimal place. So it's going to be 24. Well, let's write down the whole thing. So it's 24.8709. 24.8709. So volume of the water glass, volume of the water glass to the nearest tenth is 24.9 cubic inches. All right, so that's that. Thanks so much for taking the time to watch this presentation. Really appreciate it. If you found the contents of this tutorial helpful in your preparation for the upcoming Regents exam, do give us a thumbs up. Your positive feedback is very valuable to us. Don't forget to ask questions in the comment section below. We'll be more than glad to support you. Also, don't forget to subscribe to our channel for updates to other cool tutorials such as this. More clips can be found on Mathgotserved.com. Thanks again for watching and have a wonderful day. Goodbye.